All right. AP Physics 1. Here we go. I know you're excited for this. I know that you're ready for this, but this is the free response from 2024. If you're watching this in the future, this is my first year teaching. Okay. So 2024 AP Physics 1 Algebra Based Free Response section. This is, I've been told, I have not been told. I've heard from some students that, I show them these questions and they're like, I've never seen that before. So there may be another form out there where there may be another form out there with other questions on it. But for now, right, this is the one that we've gotten from the College Board. So we're going to quickly go over this. Okay. So this first question, a block of mass big M is released from point A, a height 6r above the horizontal. After being released, the block slides down a track as shown. When released from point A, the block does not lose contact with the track at any point. Points B and C are located at the highest points of their respective circular loops, both of radius r. All friction forces are negligible. Okay. So we start the block up here. It's going to go through the loops. It makes it through each of the loops just fine. Let's see what the question is they're going to ask. And we've got an energy bar chart. Okay. Diagram A shows energy bar chart represents the gravitational potential energy U sub G of the block Earth system and kinetic energy of the block at point A when the block is released from the height 6r. Part A, draw shaded regions in diagram B that represent the gravitational potential energy U sub G and kinetic energy K of the block Earth system when the block is located at point B, a height 2r above the horizontal. Shaded region should start at the dashed line that represents 0, represent any energy that's equal to 0 with a distinct line on the 0 energy line. Relative height of each shaded region should reflect the magnitude of the respective energy consistent with the diagram shown in diagram A. Okay, that's a lot of words, but I'm trying to read them all through so that you can at least see, right? Okay, so it says that we want to fill in this bar chart, okay, for the energy. So let's start with question 1, right? Let's identify the types of energy at each point. And I'm actually probably going to go a step further and identify the energy at each point, right? At point A, it just has gravitational potential, mgh, right? H is 6r, mg6r, okay? At point B, okay, it's now a height 2r, and not just r, because that's the radius of the circle. 2r is the complete height here. Okay, so it has gravitational potential energy mg2r. Okay, then it has some velocity because it is moving. 1/2 mv squared. We'll do mvb. Okay, for the velocity at b. And part C, okay, has gravitational potential energy as well. It's a height 2r plus another 2r, so it's mg4r. Okay, plus 1/2 mvc squared. Okay, so that's a different velocity at c, right? Okay, mg6r, right? Okay, so we see that from point A, right? We've got just GPE, gravitational potential energy. It turns into gravitational potential and kinetic. We don't know how much kinetic because we don't know the speed. We don't know the mass, right? This is entirely symbolic, okay? But we do know, at least from the gravitational potential energy, right? This is full gravitational potential energy. We are now down to 1/3 of the total gravitational potential energy, right? 1/3 GPE, okay? So going from mg6r to mg2r, that's 1/3 of the total GPE, okay? So what that means is that in the bar chart, our gravitational potential energy should be 1/3 of what it was at point A. Okay, so this goes 1, 2, 3, 4, 5, 6. So it should only go up 1/3, which is 2, right? Another way to think of it, right? If you look at the gravitational potential energy, right? This, I guess, is like multiples of r, right? 1, 2, 3. So there's 6r in the initial. Now there's only 2. Now, because energy is conserved, right? And I believe it explicitly mentions it should say negligible friction, I believe, somewhere. Yeah, all frictional forces are negligible, right? Okay, let me underline that. All frictional forces are negligible, meaning no energy is dissipated because only friction and air resistance dissipate energy, and resistance is a friction force. So that means that the remaining energy needs to go into kinetic. Okay, this is 6 here. We've got 2 here, so we need to put 4 here. 1, 2, 3, 4. Okay. You have to shade it in, right, so they can see it. Okay. Starting with conservation of energy, derive an expression for the speed of the block at point B. Express your answer in terms of R and physical constants as appropriate. Begin your derivation by writing a fundamental physics principle or an equation from the reference book. Okay. So we'll start, right? If we're trying to find the speed of the block at B, we start out with gravitational potential, mg6r, okay, and set that equal to mg2r plus 1 half mvb squared. Okay, I'm going to use VB for the speed of the block at point B. Let's call this VB. Okay. I don't know if College Board's going to get mad at you for using that, but that's okay, right? Okay. mg6r equals mg2r plus 1 half mb squared. I'm going to rewrite this as being 6 mgr equals 2 mgr plus 1 half mvb squared. And the only reason I'm writing it like that is because it makes it easier to see what I'm about to do here. Okay. If I subtract 2 mgr from both sides, because we're trying to get v sub b by itself, right? 2 mgr, we should get 4 mgr equals 1 half mvb squared. Okay. Now you want to get v sub b by itself. Okay. Well, first and foremost, before you move any further, you should see that on both sides we've got an m in common. Okay. So that knocks that out. Okay. Multiply 2 to both sides to get rid of the 1 half. Okay. So you get v sub b squared is equal to 8 gr. Okay. Now take the square root. VB equals root 8gr. Okay, there you go. Okay. No units on that. We don't want to put units on it because it is symbolic. All right, there you go, right? That's how you get the velocity of v sub b. And that should make sense to you, right? Because minimum speed required to complete the loop, right? Loop, the loop. Okay. We derived in class as being v equals root gr. Okay. That's just a general equation right here, right? That's not what you want for your answer. This is your answer right here, okay? But you can kind of get there from here, kind of, sort of, right? You can kind of self-check there. Okay, FBD time. We're drawing a free body diagram now. Okay, on the following dot that represents the block. Draw and label the forces acting as it slides through point C. Okay. Each force must be a distinct arrow starting on and away from the dot. Okay. So in order to make this free body diagram, right, at point C, okay, what's happening? At point C, the block is in contact with the loop, right, which means that there's a normal force acting on it. And what direction is it acting? Well, if the block is in contact with the loop up here, it's going down, and then also weight that acts on everything as well. Okay, so there's F sub G and F sub n. Now, this is very important, okay? These two arrows need to be drawn side by side. We are not drawing arrows on top of one another, okay? Let me just kind of messed up drawing them, right? I want to make them a little bit longer, okay? Each of these arrows, there's no on top of each other arrows. They need to be side by side. If you have something like this, okay, FG, FN, that is not okay. Okay, you can't do that. You have to do this. Okay. Student claims that 4R is the minimum height of point A such that the block can slide through point C without losing contact with the track after the block is released from rest. Briefly explain why the claim is incorrect. Okay, so just really quickly, let's use an energy conservation, right? If we start out instead at a height of 4R, okay, that means mg4r equals mg4r plus 1 half mvc squared. And you should be able to tell by inspection that that's already incorrect. But if you just actually spell it out here, right, mg4r equals mg4r plus 1 half mvc squared, right? You would notice that when you're trying to do this, right, you end up getting minus mg4r to get the speed, you would notice that it cancels out. Okay. And you would be left with 1/2 mvc squared equals 0. And mass is non-zero, right? It has some mass, so it's non-zero. Okay. That would mean that velocity would have to be 0. Okay. Okay. Let me just double check something here. Because I was double checking, make sure I derived it in terms of r. Okay, so that doesn't work out, right? So that doesn't work out. Why does it not work out? This claim, the claim is incorrect because initial GPE would be mg4r at that height at uh, at point C. The energy would have to be mg4r plus 1/2 mv squared if the block is in motion. Since no work is being done, no energy enters the system. Okay, no energy enters the system, and therefore only only GPE can exist at point C, so the block cannot move to complete the loop. Okay. Okay, there's that. All right. Question number 2. A student hangs a spring of unknown spring constant K vertically by attaching one end to a stand as shown in figure 1. The other end of the spring has a small loop from which small cylinders can be hung. In addition to the spring, the student only has access to the cylinders of unknown masses, a stopwatch, and a digital scale. Okay, perfect, because that's the only things that we need. Part A, design experimental procedure the student could use to determine the spring constant K of the spring. In the following table, list the quantities that would be measured using only the provided equipment in the experiment. Define a symbol to represent each quantity. In the space below the table, describe the overall procedure, provide enough detail so that another student could replicate the experiment, including any steps necessary to reduce uncertainty. As needed, use the symbols to find the table. If needed, you may draw a simple diagram to it. Okay. So we have only access to these 3 objects. Okay. It's going to give us the table to fill in. What are we trying to measure? What symbol are we going to use? And what are we going to use to measure? They filled in the equipment for measurement here. Okay. They don't normally do that, but they did that for you here. Okay. Stopwatch, right? What can we do? I'm thinking, here's what we can do, right? We can use the stopwatch to measure the period of oscillation. Okay. And the symbol we'll use T, okay, because that's typically the symbol for period. The digital scale we can use to measure the mass of cylinders. Okay. And we'll just call that M. Okay. Now that's the only things we have access to. We don't have the access to the cylinders, but that's going to be used in the procedure, right? We have access to stopwatch and scale. There's nothing else there. We cannot use any galvanized square steel. We cannot borrow screws from our aunt. Okay. Okay. Here's our procedure. Okay. Here's what we should do. Let's start by using the digital scale to take the mass of each cylinder. Okay. Then hang a cylinder of now known mass m to the spring. Okay. There is a way that you can do this. You can. I mean, you don't have a meter stick, right? So you can't really use kx equals mg, but that's a highly prone to error experiment anyway. So what we're instead going to do is we're going to take a mass, right? We're going to measure the mass of the cylinder, put it on the spring, bring it down just a little bit, and then let it go, and it's going to oscillate. And we can time those oscillations, okay? And then figure out the period, and then get the spring constant from that, okay? Then hang a cylinder of now known mass m to the spring, okay? Bring or pull the mass down a short distance, then release. At the same instant, okay, at the same instant, start the timer, start the stopwatch. Start the stopwatch and then time 10 up and down motions. Okay, 10 up and down motions. Then divide by 10 to get the period t. Okay. Repeat 5 times to ensure I shouldn't have said ensure, to validate data. Okay. Repeat 5 times to validate the data. Okay. Then repeat whole process with different masses. Okay. Then, oh wait, sorry. Actually, instead of repeating the whole process with different masses, let's state that last. Okay. To validate data. Use t equals 2 pi root m over k and isolate k to get spring constant. And let me also state here, replace t with experimental period. Replace m with mass of cylinder. Okay. Repeat entire process for other masses. Okay. It's a pretty long procedure, but you know what? It gets the job done. Okay. Indicate the quantities could be plotted to produce a linear graph whose slope can be used to determine the spring constant K of the spring. Okay. Trying to find that, right? We want to do a linear graph. Okay. So I'm going to do a little bit of my work up here, right? Okay. If you have the t equals 2 pi root m over k, and you want to get k by itself, okay, divide 2 pi on both sides. This is t over 2 pi. Okay. Square both sides. You get, sorry, that should be equal to root m over k. Okay. Then we'll turn this, we'll square both sides. So you get t squared over 4 pi squared. Okay. Equals m over k. Flip both sides. We get k over m equals 4 pi squared over t, and then get k by itself finally, which is just k equals m 4 pi squared over t squared. Sorry, it should be squared on the bottom here. Okay, there's that. Now, some people, right, you may not feel too comfortable putting 4 pi with m, okay? And that's totally fine. If you divide the 4 pi here, then it would give you k over 1/4. So I'm going to use two different colors here, okay, to signify the two possible responses. I'm going to be I'm going to veer on the side of caution here and say that there's two responses. Actually, I'm not even going to do that. I'm just going to give you the one response, right? This is what it should be. The linear line vertical axis should be m 4 pi squared. Okay. The horizontal axis should be t squared. Okay. The slope, rise over run. If k equals m4 pi squared over t squared, then the y-axis is m4 pi squared. The x-axis is t squared. Okay. And the slope of that graph is k. Okay. So there you go, right? Okay, in a different experiment, a student attaches one end of a spring to a force sensor that is attached to the wall. The other end of the spring is attached to a cart with mass m equals 2.25 kilograms. The student places a motion detector to the right of the cart, as shown in figure 2, pulls the cart to the right a small distance so the spring is stretched. Student releases the cart from rest and it oscillates. So what we do is we take the cart here, we pull it to the right a little bit, it goes, and now it's going to oscillate. Okay, and we graph the velocity versus time and the force versus time. You can see they're both sine waves. Okay, sine or cosine waves, which makes sense for simple harmonic motion. Using the data in the velocity time graph, calculate the change in kinetic energy of the cart from t equals 0.5 to t equals 2. Okay, well, if we're talking about change in kinetic energy, right? Okay, that's 1/2 m delta v squared. Okay, the change in velocity, right? Okay, or what we can do is we can do delta is equal to delta ke is equal to ke equals 1/2 m v final squared minus 1/2 m v initial squared. Okay, so and the final velocity, so the velocity, right, at t equals 0.5 and the velocity at 2 seconds. Okay, let's go back to the graph and look. Okay, velocity at 0.5 is 0.3. Okay, so 0.3. Okay, velocity at 2 seconds is 0. Okay, okay. The so right here, right, we've got initially, right, or sorry, at the end, it's not moving at all, which means that there is no kinetic energy. So that means that delta ke is going to be equal to 0, right, because that whole thing becomes 0, and subtract from that the initial velocity, or sorry, the initial kinetic energy, which is 1/2 m. M is given to us, I believe, in the earlier part, should be 0.25 kilograms. Okay, 0.25, and then the initial velocity is 0.3. And so we're going to get a really small number here. And let me get my calculator because I forgot to get it out for this. Okay. Okay, you can get your calculator out. It's probably just going to be best to calculate in that. Okay. It's going to be, let's see, 1/2 times 0.25 times 0.3 squared. And that gives you 0.01125 joules. Now, actually negative, okay? Make sure you don't forget that negative right there, okay? Because this is 0 minus that, right? You're losing kinetic energy. You're starting out with some and then you're going to 0. Okay, using the data in the force time graph, estimate the change in the kinetic energy of the cart from time t equals 0.5 to t, or sorry, 0.5 to 2.5, okay? Estimate the change in kinetic momentum. Okay, change in momentum. You got to understand these definitions, these keywords right here. Change in momentum. That's impulse. Okay. You also got to understand that if you're trying to get impulse from a force time graph, you got to take the area. Okay. To take the area under the curve. And we're going from 0.5 to 2.5. Okay. So from 0.5 to 2.5, okay, we take the area under the curve. Well, the area is bounded here, and the area is bounded here. Now, the beautiful part about this is you can try and break it up into two triangles and take the area, but you don't need to, because hopefully you should recognize that the amplitudes are the same, the period is the same. Therefore, this right here, these areas are equal. You've got a section of negative area, you've got a section of positive area, okay? So, therefore, the positive area is equal to the negative area. Therefore, the change in momentum from those 2 points should be 0. Okay? There should be no change in momentum. Does the data from the velocity time graph support that claim? Let's find out. If there is a, so again, right, delta P is also equal to M delta V, right? Okay. So does the velocity change on those 2 points, right? Well, V at 0.5, we've already established is 0.3 meters per second. What's V at 2.5, though? Let's find out, right? V at 2.5, can you see, is also 0.3. Okay. That means that delta V is equal to 0. No change in velocity means no impulse. So, yes. Our estimation, yes, our estimation is supported by the VT graph. Okay, I'm writing really sloppy here, right? I'm writing the exact same things that I'm saying. Okay, that's question number 2. Question number 3. I will tell you this. This is easily the hardest question on this whole test. Okay. The left end of a uniform beam of mass M and L is attached to a wall by a hinge. Okay, I'm just quickly flipping through. Yeah, it's easily the hardest question. Okay. Left end of a uniform beam of mass M and L is attached to a wall by a hinge, shown in figure 1. One end of a string with negligible mass is attached to the right end of the beam. The other end of the string is attached to the wall above the hinge at point 1. The beam remains horizontal. Hinge exerts a force on the beam of magnitude F sub h, and the angle between the beam and the string is theta equals theta 1. Okay. Following rectangle represents the beam in figure 1. On the rectangle, draw and label forces, not components, exerted on the beam. Draw each force as a distinct arrow starting on and pointing away from the point at which the force is exerted. Okay, so this is an extended body diagram. This is an extended body diagram. I think they should use that terminology. Okay. But what it's asking us to do is to draw and label the forces, and it should start at the point of which the force is exerted. Okay. Most obvious one, gravity, right? Gravity acts from the center of mass. Okay. For an extended body, it's in the center of mass. I mean, for everything, it's the center of mass, right? The tension force is also very obvious, right? It should go up and to the left, right? You don't write your angle on this, okay? And finally, the hinge. Now, a lot of people, when I actually looked at this problem initially, I thought the hinge was going to act straight to the right, right? It actually doesn't. It gives it a force that is equal in magnitude and equal in angle on F sub t. So it should also go up, right? And I probably didn't draw that super well, but they should be equal in magnitude, right? The force of the hinge should be equal to the force of the tension, okay? The angle that the hinge acts on should be equal to the angle that the tension acts, okay? So it should be the same, okay? That's all you have to draw on that body, on that diagram. Tension, gravitational force, the force of the hinge, okay? Now it's going to move the rope, the string, to a lower position on the wall, okay? If it moves to a lower position of the wall, then the new angle is theta naught, okay? Or sorry, theta 2. I don't know where I'm getting theta naught from, okay? The magnitude of the tension in the string in figure 1 is Ft1. The magnitude of the tension in the string in figure 2, Ft2. Indicate which of the following correctly compares the two, okay? Okay. So think of it like this, right? Think of it like this is a door that you're trying to open, okay? If these two, right, if you're trying to open a door, right, and you pull on it with a string of this angle, it's going to open a lot easier than it would if you pull on it with this angle, right? Okay, think about the torque, right? The torque, okay, if rod is in equilibrium, right, the torque going clockwise must equal the torque going counterclockwise, right? Okay. Just realized the light wasn't on here, and that's not really going to change anything. But yeah. Okay. A torque going clockwise has to equal the torque going counterclockwise. Okay. If the hinge is exerting the same amount of force as the tension, then really it's just going to say that the torque, right? Which one's going clockwise here? So it should be gravity is going clockwise, right? R F sub g sine theta equals, and then you've got the hinge, right? Or sorry, the hinge and the string acting. Okay. So it's got two. I guess if we're taking it about the pivot point, it would just be the if we're doing just the pivot point, those would act away from the pivot point. So therefore, it would just be the tension, right? R F um, R F T sine theta. Okay. You don't even really need to do this part right here, but if the torques balance out, okay, then if the torques balance, right, then R F T sine theta must be equal to mg. Okay. Sine theta, if theta decreases, sine theta also decreases. Okay. So if theta decreases, sine theta also decreases. Meaning Ft must increase to satisfy RFT sine theta equals mg. Okay. So therefore, tension 2 should be greater than tension 1. Okay. Okay, derive an expression for the magnitude of tension in the string. Express your answer in terms of m, theta, and physical constants as appropriate. Begin your derivation by writing a fundamental physics principle or an equation from the reference book. Okay, so we'll start off with Newton's second law in rotational form, which is just RF sine theta, right? Okay, so we start with R. You should start right with R, as I said earlier, F G sine theta. Okay. Now, this is for the net force, right? The net forces on this beam should all cancel out as well, right? So that means all the counterclockwise torques and all the counterclockwise torques should be balancing each other out. All of the clockwise torques should be balancing each other out, right? So then it should be R, F, T, sine theta, right? These two should be balancing each other out to keep it from moving, right? Okay. The hinge is our pivot point, so we don't really need to consider its torque, right? Okay. We want to get F sub t by itself, okay? But we can further simplify F sub g as being mg, right? R mg sine theta equals R ft sine theta, okay? It's important to note that the R here for the gravity is halfway from it, right? If you look here, gravity is acting halfway at 1/2 L. Tension is acting at the full L, okay? So we'll replace our R's here, okay? This is 1/2 L mg sine theta equals L ft sine theta. And I guess I should make it clear this is capital M because it wants me to do it in terms of M, right? Okay. You have an L on both sides, right? Easy cancellation. Okay. You also have a sine theta on both sides, right? But we're not going to cancel that one out quite yet, okay? Because we don't want to we don't want to cancel those two out yet because the theta is not the same, right? But it's important to note, right, that for the gravity, right, sine theta is equal to 90, which means sine theta would be equal to 0. Or sorry, equal to 1, not 0, sorry. I'm thinking of cosine. This is equal to 1. So that means that this sign cancels out, but you can't cancel out the other sign. Okay, so you're left with 1/2 mg equals ft sine theta. Okay, divide sine theta on both sides. You can rewrite this as being ft equals mg, okay, 2 sine theta. And that is the expression for the tension. Okay. Okay. Okay, is your derived equation in part C consistent with the justification in part B? Okay, well, let me rewrite the equation real quick, right? Force of tension equals mg, capital MG, over 2 sine theta, okay? Okay, mg over 2 sine theta, right? In part B, we said that as theta approaches 0, the tension force approaches in, I'm just going to write infinity, right? It gets larger as it goes, right? This equation supports the justification Okay, this equation supports the justification, EQN, supports the justification because ft and sine theta are inversely proportional. Okay. As theta approaches 0, the value of sine theta also approaches 0, meaning the value of ft increases. Okay. And you can also state, right, it's because it's in the denominator, right? If the denominator goes down, then the value is going to go up. Okay. This equation, or this right here, this is angular speed and angular time, or sorry, angular speed, not angular time. That's not a thing. Angular speed versus time, right? The way that this graph is going to look, okay, so they cut the string, the beam begins to rotate about the hinge with negligible friction, okay? Sketch the angular speed of the beam as a function of time for the time interval while the beam falls, but before it becomes vertical. This is just going to look kind of like this. Okay, it's going to look kind of like that. Reason is because this is simple harmonic motion. Okay. Okay, it's a simple harmonic motion, so it's going to have to be a sine or a cosine curve, right? However, at the top here, it becomes vertical. When the beam becomes vertical, right? The speed is going to change its direction, right? It's going to hit its maximum speed at the very bottom, then it's going to start to slow down, right? So you would expect this to go down, but this only wants us to go before the beam becomes vertical. So this is just before it becomes vertical. It's going to speed up, speed up, speed up, and then slow down. It's kind of start to slow down as it goes, right? Okay. And should know the shape just because it's simple harmonic motion, right? At the bottom of its swing, right, it's going to hit a peak in the graph, right? Okay. A question with the pendulum, right? We've got a small sphere. Simple pendulum consists of a small sphere that hangs from a string with negligible mass. At the top end of the top end of the string is fixed. Okay. Top end of the string is fixed. The sphere is pulled to point A so that the string makes a small angle theta with the vertical as shown. The sphere is then released from rest and swings through the lowest point at point B. The work done on the sphere by Earth is W sub E. The pendulum is then taken to planet X. Planet X is the same as the mass of the Earth, but radius is greater. Okay. The sphere is then brought up to point A, let go, it's displaced the same theta, released from rest, swings through those point B. The work done is W sub X. Okay. Justify why W sub X is less than W sub E. Okay. Well, first off, right, the gravitational field strength of a planet is given by G equals big G, big M over R squared. Okay. We derived that using Kepler's laws in circular motion, right? There's a derivation for it for Kepler's law. Okay. If sorry, not gonna say if, I'm just gonna say both planets have the same mass. Have same mass. Okay. But plan X has more radius. Okay. More radius. Okay. Meaning G is lower for plan X versus Earth. Okay. G is lower for planet X versus Earth. Okay. If G is lower, then F sub G is lower. Okay. If G is lower, then F sub G is lower. Okay. And then if work is F D cosine theta, and D and theta are constant, work only depends. I know I'm yapping a lot here, right? But I'm trying to make sure I answer the question fully. If work is FD cosine theta, D and theta are constant, work only depends on the force. Okay. So Wx would be less. Okay. And I should probably say here, if G is lower, Fg is lower on planet X. Okay. Okay. A new pendulum was made by hanging the same small sphere from on a different string with negligible mass. The new string is slightly elastic. The length of the string may decrease or increase depending on the tension applied to it. On Earth, the spring is again displaced theta from the vertical, released from rest. New pendulum oscillates with period t sub e. The new pendulum is then taken to a different planet, planet Y, and the radius of planet Y is the same as the radius of Earth, but the mass of planet Y is larger than the mass of Earth. On planet Y, when the sphere is again displaced from the vertical and released from rest, the pendulum oscillates with period ty. Explain in a paragraph how ty could be larger or could be smaller than te. Okay, so this is an interesting question because it can go either way. Okay. If planet Y has same radius but more mass than Earth, okay, then planet Y has a stronger G field by the equation G equals big G big M over R squared. Okay. Therefore, by the equation T equals 2 pi root M over K, okay. So therefore, by the equation T equals 2 pi root M over K, oh, no, wait. I'm thinking of a spring mass oscillator. Dang it. This should be root L over G, right? Because that's a pendulum, okay? By that equation, okay, if G is stronger, the period must be shorter. Okay. However, okay, if G is stronger, the force of gravity F sub G is also stronger. This means that weight is stronger. This means the object weighs more. Okay, which can lead to increased tension. Okay. More tension, due to the nature of the string, okay, more tension means the string may stretch. Okay. If the string stretches, okay, if the string stretches, then length is increased. If length increases a considerable amount, then by t equals 2 pi root L over G, the period of y may be larger than period on Earth. Okay. Oh my gosh. Okay. I'm doing so much writing here. Usually when I go over these, I just hit the main points, but I'm going to write the whole paragraph. Okay. Okay. So in general, right, there's two different ways it can go, just due to the nature of the string. Okay. Make sure you know that. Okay. Question number 5. We're finally on the last one. This is exciting. Okay. At time t equals 0, block A slides along a horizontal surface towards block B, initially at rest. As shown in figure 1, the masses of blocks A and B are 6 kilograms and 2 kilograms respectively. The blocks collide elastically, and it's got that even underlined for you, elastically at t equals 1 second. As a result, the magnitude of the change in kinetic energy of block B is 9 joules. Okay. All frictional forces are negligible. Okay. Oh, that's also really important. Okay. Okay, the change in kinetic energy is 9 joules. Well, let me tell you this, right? Oh, actually, let's read the question. Determine the speed of the block B immediately after the collision. Okay, well, the change in kinetic energy for block B is 9 joules. Okay, well, initially, block B is initially at rest, right? So it has initially 0, and the final kinetic energy is equal to 9. Okay, 9 joules. Okay, now that means that the change in kinetic energy, so the final kinetic energy is 9 joules. There's two ways that you can do this, okay? Actually, there's only one way. I'm going to do the easy way, right? Okay, if the kinetic energy at the end is equal to 9 joules, right? You also know that kinetic energy is equal to 1/2 mv squared, right? Is you're trying to find the speed of block B after the collision, okay? Kinetic energy, we know that kinetic energy is 9 joules, okay? We're given that in the problem. 1/2, we know the mass of the block is 2, and then we're trying to find VB final. Okay. Okay. Right here, you should notice this is going to be a very easy problem. 1/2 times 2 is 1, so we can disregard that, and then you get VB final, okay, squared equals 9. And what squared gives you 9? VB final should be 3, right? And you can use a calculator for that if you so wish. Okay. Okay. That's easy peasy, right? Easy money right there. Okay, the graph in figure 2 shows the positions of X of block A, B, and the center of mass of the 2-block system. Oh, that's great. We are given a center of mass problem. Okay, that's fun, right? I love center of mass problems because guess what? 90% of the time, they're trick questions, okay? So we are given, I'll use green for block B because I used that in the previous part. I'll use blue for block A, red for center of mass, okay? Okay. The 2-block system as functions of t between t equals 0 and t equals 1 second. On the graph in figure 2, draw and label 3 lines to represent positions of A, B, and the center of mass of the 2-block system as functions of t between 1 and 2 seconds. Each line should be distinctly labeled. So it gives us from 0 to 1. Now we want to fill in the remaining part, 0 to 2. Okay. Well, B is easy to figure out because B, we solved the velocity after the collision, right? 3 meters per second. This is your slope, okay? Because look, This is a PT graph, position, time. That slope, that means that for the second section, you're moving 3 meters in 1 second. You will rise 3 meters before you run a second, right? Okay, so that means that from 1 to 2, you're wherever you're going to start out, you're going to move 3 meters. Okay, so you start at 2, you're going to end up at 5 at 2 seconds. Boom. Okay, use a ruler or a straight edge here. Okay, so start at the point, right? Get that lined up. Okay, boom, boom. Okay, beautiful. Label your arrows or label your lines, right? Block B, even though I'm color coding them. You probably aren't going to color code them on the AP exam. Label them, right? Okay. Block A, right? Oh, wait. We don't know the final velocity of block A, right? We need to figure out the velocity of block A. Okay. Well, we can do that with conservation of momentum, right? Because guess what? MVA equals MVA final plus MVB final. Okay. All we got to do is plug everything in. Now, here's the thing, right? We don't know what the initial velocity of VA is. We're not given it, but we can solve it because look, it's a PT graph, right? Take the slope of this line right here. Okay. In 1 second, we go 2 meters. Okay. Rise of 2, run of 1. So that's just 2, right? VA initial is equal to 2 meters per second. Okay. So M, and I forget what the masses here are. M, so I should make this clear. MA, MA, MB. Okay. I forget what the math. Oh, so here we go. 6 and 2. Okay. Okay. 6, 2 equals 6. We don't know what that is. Okay. And 2, and the velocity we already got was 3. Okay. Do your conservation of momentum here. This should give you 6 times 2 is 12. Okay. Equals 6 VAF plus 2 times 3 is 6. Okay. If you subtract 6 from both sides, you get 6 equals 6 VAF, and it doesn't take a rocket scientist. I may be one, but it doesn't take a rocket scientist to figure out what VAF is going to be. That's just going to be 1 meter per second. Okay. So now you're going to go 1 meter. So block A is going to traverse 1 meter in the next second. So from 1 to 2, it will then go 1 meter from where it starts. So it'll go right there. Okay. Use your ruler again to draw this line because you want it to be nice and straight. Okay. Okay. This is block A. Okay. Now, we did learn about in this class, we did in my class at least, we did learn how to calculate center of mass and the speed of the center of mass. But you don't have to do all of that because that's a lot of work, right? You don't have to do all of that. Why? Because there's no unbalanced external forces that act on this system for any noticeable amount of time. It tells us that there is no friction, right? All frictional forces are negligible, which means that there is no unbalanced external forces. The collision itself is not an unbalanced external force. It's all inside of the system, which means the center of mass, right? Remember, momentum is conserved in every collision. The center of mass keeps its motion, again, unless there is an unbalanced external force. So the center of mass should look basically, oh, I'm trying to draw like a dotted line, but my hand keeps shaking. Okay, it looks kind of like that, right? Right, there's that red line right there is your center of mass. It should keep its motion. It should not change its motion at all because there is no unbalanced external force. Okay, part C. This is the very last part, and then you'll be done. Right? Okay. Consider if in the original scenario, instead of colliding elastically, the blocks collided and stuck together. Okay. Consider if they collided and stuck together. That means it's a perfectly inelastic. Okay. Describe how the line drawn for the center of mass in part B would change, if at all. Briefly justify your response. Well, guess what? It doesn't matter what type of collision, still conserved. Still no unbalanced external force. Even if they stick together, still no unbalanced external force. Therefore, the line would not change at all. Would not change. Because no matter the collision, okay, because no matter the collision, no unbalanced external forces are acting. Act on the system for a noticeable amount of time. Okay. Oh my gosh! All right, we did it. That's all the questions on there. I don't think it's too bad, right? There's all 5 questions there. Okay. There you go. Right. Hopefully, you're not screaming or breaking your computer saying that you did something wrong or whatever. Right. So there you go. Right. Could be wrong. If you have any thoughts or anything, you're welcome to reach out. Okay. All right. Peace out.